Okay, so here's what we were talking about last time. I'm gonna make one last little quick comment on this example that we've already mostly talked about before going on to the next one. So the comment I wanted to make is about what this example shows about an earlier comment that I made. And an earlier comment I made, let me go back to, for example, something like this. A lot of students feel like, well, look, you can kind of look at the algebra that's given in the statement of the question, and you can just kind of see what these bounds are going to be just from the way the algebra is stated. And some of y'all have had multivariable calculus classes in high school, and sometimes that is how it is presented, that you should find bounds for iterated integrals in some multivariable calculus classes in high school. What I think this example shows is that is absolutely not a reliable method. Right? It's just not. I mean, there's no way that you're going to be able to just at a glance kind of look at the structure of the algebra there and then just kind of say, oh, yeah, so, what you do is, you take this formula, and this formula goes into that bound, and this formula goes into that bound. It's just not going to work, right? Because you can't see from what's, from just, just the structure of the algebra, where this corner is going to be and how that's going to affect your slicing process. You just can't do it. Doesn't make sense. Right, yes?
And just from looking at that's the shape it takes?
No, well, we had a conversation last time about how you use this information to make this picture. Yeah, and it's a process. Yeah, right. So the point is, you need this picture, right? You need that picture to be able to identify that there is a corner here that will cause problems if you do your X slicing on the outside, or if you do your Y slicing on the outside. So I just want to make it clear, in this course, when you write down an iterated integral to compute a triple integral, likewise for a double integral, you basically have to have a picture. And it's not that sometimes you won't get the right answer if you do it without a picture. That's not the point. The point is, if you do it without a picture, then you've given no actual legitimate mathematical argument, no reliable, deductive reasoning kind of argument to justify your answer. Right? And again, I remind you, this is not a class about answers. It's a class about reasoning. It's a class about ideas. Right? So you got to give me a picture. Without a picture, I consider your answer largely unsupported. Okay. All right. And side note, if you're not motivated by that, then there's also the little matter of the fact that you'll get wrong answers if you, if you try to just look at this algebra and I'll just write something down that looks based on that algebra. Yeah, you're going to get wrong answers sometimes, often, in fact. Okay. All right, moving along. So next example, I want to go through. Again, we're going to skip the details, but I want to talk about the big points. Suppose you're looking at a domain that's bounded by these two paraboloids. Now, these are clearly paraboloids, right? You can see the rotation in the nature of the formulas. You can think about their cross sections and make a rotation argument, etc. And what you end up with is that this. I keep circling the wrong thing. There we go. This is a paraboloid that looks like kind of like that, right? And this is a paraboloid that looks kind of like that. And so the R that's bounded by those is, it's going to be tough to draw, but it's this thing. It's kind of in between them. Now, let me emphasize, the way that I've shaded the yellow there doesn't really get at the entire R, because there's also some, it's got a kind of a side around there, right? And there's also this back of it. And so it's a pretty tough thing to draw a picture of. Nevertheless, we can sort of do our best. Okay. So suppose you want to do a triple integral over this region. What do? And there's different ways to look at it. One thing you can do is you can notice that it's a lot easier to solve for y. In fact, we have already got solved for us y in terms of x and z, and that motivates putting dy as your inside differential, right? Your inside integral. So that's one way to think about it, right? But then there's the whole matter of the slicing. And you can see from the picture that this is going to be weird if we were to do it the other way, if we were to do dy slicing first, right? If we're slicing perpendicular to the y-axis. Everything seems fine and dandy until we get to this point where, well, it's not exactly a corner, but the nature of the y slices changes pretty dramatically beyond that point. Right? So something weird happens. Yeah. Okay. So we want to slice one of these other ways, but I mean, here's what it gets really tough to draw the picture, though. I mean, let's take a z slice, for example, of this solid. Oh, golly, artistic challenge here. I'm not. I mean, again, this is not my first time, so I can kind of go through, and I mean, I think I can persuade you that slice would look something like that, right? But that's tough to see, and tougher to draw. Okay, so let me remind you, when the situation allows for it, as in this case, think about the projection, right? So we've already decided that we want to do dy on the inside. That leaves x and z on the outside. Notice that the projection of this solid into the xz plane is nice and easy, right? It's just a disk. So as we're going through and thinking about, what would it look like when I slice up the, if I take a z slice? Well, that z slice is really, really hard to draw on the solid itself. Something like that. Right? It's a really hard thing to draw. But on the projection in the xz plane, well, no sweat. It's just a little segment, right? Nothing to it. Right? It's a lot easier to understand the projection than it is to understand the solid itself. Now, furthermore, one other important little asterisk on this, we don't want ugliness to project its way into our simple shadow or projection in the xz plane. So let's further notice that not only is the projection nice, but every point in the projection, the corresponding range of values that we're going to have for y, when we get to that dy integral, the picture is a nice simple line segment. This lower bound, again with the elbow, this lower bound determined by that point is entirely on that surface, nice and easy equation, right? Likewise, the upper bound is going to be determined by that point, which is on this surface, which has that nice, easy equation. So it's not just that the projection looks good, but furthermore, what that's going to lead us to on the inside integral, also nice and simple. Okay. So look for opportunities like this, right? Now we don't have to deal with this great, big, ugly three-dimensional picture. I'm just going to say, well, let's just look at the projection. That projection is easy to identify. It's going to be based on where do these two surfaces intersect. These two surfaces intersect where both of those equations are true, and namely, therefore, where x squared plus z squared is 4. And it's much easier to just think about that projection here. Becomes a section 14.3 problem, right? We're just looking at a disk and slicing up a disk. We've done that a million times before, and so these x and z bounds are easy. Yeah.
Why can't we find the two volumes separately and then subtract them?
Well, for one thing, we're not computing volumes. We're computing an integral. But now we could compute the two integrals separately and subtract. But again, what we're doing here is this is mathematical weightlifting, right? So I'm trying to point out how to use an idea that allows you to solve problems, and the fact that there is a way to bypass that in this case is it's sort of like, why lift the weights? Why not use a forklift? Yeah, because we're building muscle here, right? So yeah, in this case you can, but I'm trying to point out a tool, how to use this tool. Yeah, right. Yes.
Did you mean? I don't understand the 2x squared plus 2y squared.
Oh, so this paraboloid? Yeah, so it's an old chapter 12 idea. The point is this is rotationally symmetric around the y-axis, and you can look at a particular cross-section and argue that it's a parabola. And, yeah, a bunch of chapter 12 details.
Can you set it equal to the other y, though?
Mm-hmm. Yeah, so if these two equations are both true, we're looking for points where these two y's are equal, right? And if those two y's are equal, that means that this is equal to that, which is what this says.
There's not a y there.
I'm sorry, what now?
The thing you circled and pick at the bottom.
Oh, I'm sorry. Okay, in the several years that I've been using these notes, no one's noticed that typo before. Thank you for noticing that. This should be a z. Thank you for catching that. That indeed should be a z. I totally misunderstood your question. Yeah. So, right. Okay, everybody, change this in your notes, please. If you're working off of my notes here. Okay. Right. So anyway, keep that in mind. This projection tool is a very nice tool. Now, one little last detail: we do have to think about the y bounds, and again, that sometimes the fishes jump in the boat. For a given value of x and z, let's say there, the lower bound is determined by that point. That point is on this surface. That surface has this equation. Solve for y. Oh, good. It's easy. It's already solved for. Right. The upper bound is determined by that point. That point's on this surface. This surface has this equation, right? Solve for y in that equation. Again, good news, it's already solved for. And that gives us our inner bounds for our y integral. Yeah. Okay. All right. So there's countless different examples of three-dimensional solids that you can slice up and with various considerations of, avoid corners, try to solve for the easy variables, think about possible projection, tools. And so give yourself lots of practice on those. The homework will do some of that for you, of course, right? But make sure that you're comfortable with all the ideas, all the different sort of twists and possible pitfalls and landmines and stuff. Okay, some applications. I'm going to be really fast on this because it's just like with double integrals. Center of mass. Right, just like with double integrals. Now, of course, if we're talking about a three-dimensional solid, the center of mass is a point in three-dimensional space. It therefore has 3 coordinates. And by arguments highly analogous to what we've already done, these are the formulas for the coordinates of the center of mass. Centroid. Moment of inertia, same deal, and I forgot to make this a triple integral. But moment of inertia, same deal. Right? You can talk about if you have a three-dimensional solid that's rotating around some sort of an axis, and if you wanted to write kinetic energy of that in terms of angular velocity instead of linear velocity, makes more sense, right? Then this is the formula for the angular analog of mass, aka moment of inertia. And so it's still, you'll notice, integral r squared dm. It's just a triple integral now. All the ideas are totally the same as we did before. Let me remind you about this r thing, right? Depending on what axis you're rotating around, right? If you're rotating around the z-axis, let's say, and you've got some solid like that, and a particular point in that solid, and you want to talk about the distance from that point in the solid, where you are in the solid to the axis of rotation. Well, that distance, draw the picture. Draw the actual, the rotating arm, you might say, but the shortest distance from that point to that axis, and the geometry of the picture will tell you what the formula is then for that distance. Right. So please don't just memorize formulas for r. It's different depending on every axis that you might be rotating around. You might be rotating around a coordinate axis. You might not. Right. So formula is going to be different every time. Let the geometry guide you for that r. Okay. All right. Okie dokie. Symmetry, just like with double integrals. I mean, it's really, really very similar. A little bit different, of course. Three-dimensional domain. We're in a three-dimensional world. We don't reflect through lines. In three-dimensional worlds, we reflect through planes. It's the same concept, though, or reflection. Right? And through a plane. I would argue, in fact, it's an even more familiar concept. After all, the most common reflection that we experience in our everyday lives is in the mirror, which is a plane, right? This is really the more familiar construction of a reflection. Okay. Analogous, we have the notion of odd symmetry. Odd symmetry just means that you get a minus sign on the function when you reflect. We can talk about what it means for a domain to be symmetric. It mean, just like it meant in the two-dimensional case, it means that a point is in your set if and only if the reflection is in the set. Same idea. And we get a highly analogous theorem. If you're looking at an integral, and if the function has odd symmetry, and if the domain is symmetric, through that same plane, I cannot emphasize enough, it's got to be the same plane, right? Then your triple integral is equal to 0. And that's a huge win, right? We don't have to slice and dice, think about bounds, draw pictures of slices, consider the possibility, fingers crossed, hopefully a projection maybe or something. Deal with all of the resulting integrals that, there's 3 single variable integrals to be dealt with if you do a triple iterated integral. It's a huge pain. Snap your fingers, integral equals 0 by symmetry. It's totally awesome, right? Big fan. Same rules apply if you cite this theorem. We'll get to that in a minute. Why is this theorem true? Same argument, right? If you have a reflection through a certain plane, let's say this one, right? And if you have a domain that has the desired symmetry and if the function has odd symmetry and all the usual setup, well, the pieces pair up. That piece and this piece, its reflection, right? The values of the function are opposites. They pair up because the domain is symmetric. Everything disappears in a puff of smoke. Same exact argument that we made for double integrals. It's just 3-dimensional now. Okay. All right. So let's see an example. Suppose we want to compute this triple integral here. Let's take a moment to dwell on the nightmare that this integral would be if we didn't use a symmetry argument. There's trig in it, and that's, I guess a little unfortunate, right? But notice we're talking about an integral over the unit ball. Let's roll back into the notes through where we talked about integrals over the unit ball, right? Here's what a unit ball looks like, and we did the slicing and dicing, and check out all the square roots. It's a nightmare, right? All of these square roots here that are in the bounds of the inner integral, those are going to be in the integrand of the second integral. Square roots in your integrand stinks, right? And then if you make your way through that, well, then these bounds on that second integral are going to be in the integrand of your outside integral. So you just got, it's a nightmare of square roots and trig, and it might not even be tractable. I don't know. I certainly don't want to play with it. So let's try something else. Notice if I were to choose the XZ plane, right? The formula for reflection through the XZ plane. Easy to write down, easy to see from the picture. After all, if you reflect through the XZ plane, the X and Z coordinates don't change. Perfectly clear from the picture. The Y coordinate just becomes the negative of what it had been. Easy argument. And then notice this reflection, when you plug that reflection into the function, right? You get the required minus sign, and so this function has odd symmetry through that plane. And of course, now it's geometrically clear that the domain is symmetric through the XZ plane. You gotta love spheres. Spheres have every symmetry pretty much that you could hope for, right? They're awesome. So the conditions of the theorem are satisfied, and we don't have to slice and dice. We don't have to integrate and deal with square roots and trig. No, an integral is 0 by symmetry. Big win. Okay. Alrighty. A couple of quick comments. if you were do a symmetry argument, and I encourage it, right? I'm a big fan. If you do a symmetry argument, you do have to give me the necessary details. You can't do the Hail Mary pass. We've got 10 seconds left on the exam. Integral equals 0 by symmetry. Come on, symmetry, right? Right. So you got to give me the usual information. You got to give me what plane are you claiming symmetry through? What is the formula for the reflection through that plane? I want to see the complete argument that the function has odd symmetry. I want to see a valid assertion. You don't have to justify it, but a valid assertion that the domain is symmetric, right? And then, declare victory.
Is a unit ball just a sphere?
I'm sorry?
Is a unit ball just a sphere?
So it's another one of these lingo things. The sphere is the surface, right? So we live on the surface. The surface of the Earth that we live on is a sphere. The Earth itself is the ball. It's the solid inside, right? So if you're doing a triple integral, your domain's got to be a solid ball. Yeah. Right. Okay, so make sure to give me all the necessary details. Last quick comment. How did I know to use the XZ plane? And let me remind you, very often you can just kind of reverse engineer the idea. We can look at this integrand right off the bat. Let's see, let me come over here and come back in. Look at this integrand, and you can just start speculating what kind of thing, what reflection formula that I hope I can make happen would actually make this function be odd. Right? What can I do to this that looks like a reflection that would turn this into the negative of what it otherwise is? So, first attempt, you might ask, well, what if I stick a minus sign on the x? Does that do it? Nope. That minus sign gets squared. So, changing x to negative x doesn't do anything. But if you change z to negative z, well, there's no z's in the formula, so again, nothing happens, right? But then you notice that if you put a minus sign on the y, and you can see it happen in the algebra, right? But you can also kind of see it's going to happen there. The y squared will make the minus sign go away, but sine y turns negative if you stick a minus sign on the y, right? So the reverse engineering that you do is the formula motivates the formula for your reflection. And then the reflection formula motivates the choice of plane. Right, so strategically, I expect that's how you're in practice going to do it. Make sure, don't forget to confirm once you've done this that the plane actually is a plane of symmetry of your domain. Again, it's absolutely essential and critical. Both of the conditions have to apply through the same plane. And I remind you, symmetry arguments are awesome, totally awesome, but they are also dangerous. They are, if you claim a symmetry argument where it does not apply, then nothing you've written down on the page is both true and relevant to the actual solution to the problem, and there's just no way to give partial credit. So be careful. Make sure that you're clear that it really is a valid argument, and double check your minus signs and your formulas. Okay. Alrighty. Okay, so on to a new subject, change of variables. Now, this is not the next section of the book. I bounce around a little bit in chapter 14 for reasons that I will make clear a little bit later on. But we're jumping all the way up here to section 14.9, if I remember correctly, change of variables. I'm going to try to motivate the formula that we're about to make a lot of use of. It's a very powerful formula, huge even, right? And in order to be able to motivate it, I have to throw a couple ideas down first, just to kind of lay groundwork, context. First observation I want to make: when you do an integral, as long as the function is appropriately nice, and I don't want to get into the weeds of worrying about that. So everything we're going to do in Math 212 is integrable. Everything's fine. The way you chop up your domain does not have to be regular. Now it was when we wrote down back in a Calc 1 class, if you look back at the way integrals are defined, we take that interval and we slice it up, delta x is b minus a over n, and all the pieces are exactly the same size. We do that out of laziness. There's really no need for it. Right? It makes our lives easier b minus a over n. Nice simple formula. Get to use it everywhere. That's convenient for us. But it's not actually important. I will argue, for example, if you have a mass on a rod, and you want to compute its mass by chopping it up into little pieces, it is not essential that those pieces all be physically the same size. I mean, if you chop a rod up into little pieces that are a little bit different in sizes, put them on the scale, it still adds up to the total mass, right? So there's no requirement, really, that the pieces be the same size. And if you want to make them conspicuously different sizes like I did here, okay, that's cool. There's no problem. We still define integrals that way. Just a little weirder, a little more trouble. Doesn't matter. Okay. Okay. Here's another reminder I've got to throw at you to lay some groundwork, create a context. Y'all remember the substitution rule, I hope. There it is. Again, Calc 1. Calc 1, Calc 2, depends on the class. And the idea is if you write down u equals g of x, then you do a little algebra, du g prime dx, and off you go, plug and chug. Right? Side note, don't forget you got to change the bounds, right? These bounds are values of that variable. Likewise, then these bounds have to be the corresponding values of that variable. So, in other words, don't forget to take these x values and, in fact, plug them in for x, thus getting u values that are your bounds for your du integral. Okay, so I hope that looks familiar. I want to give you a different point of view, something that's going to be more useful for us for analogy purposes on how this is. I want to think of this g not as an algebraic tool, but think of it as a function that is physically, well, at least geometrically, that you visualize as having a domain way over here and a target way over here. I want to geometrically represent the action of that function. Okay. So in fact, you go back to these integrals here, and you notice here you have an integral, du integral from g of a to g of b. Well, yeah, here's that domain. That is that domain. You've got an integral on the u-axis, and those are the bounds on that integral. Likewise, over here we have a dx integral from a to b. Well, yeah, right. Well, there's that domain. You can see that what this function g is doing is it's like it's physically lifting up that green interval and sort of setting it down on its image, which is this purple interval. Okay. All right. Let's throw some details at this. This function, right? If you have a domain there and its image there, well, hopefully no surprise when you chop up the domain there on the left, in effect, that chops up the domain on the right somehow. Right? Every one of these points individually, like that point there, has as its image that point over there. So whenever you do a partition of the x interval, you are implicitly, in effect, partitioning the u interval. Now, irregularly, of course, right? This g function could be all kinds of wacky, so this isn't going to be an even partition. But per our earlier note, who cares? Doesn't matter. Okay. So if I want to do an integral on this domain over here, I can use this partition. I can take little pieces like that, right? Chop up, add up in the usual way. A little harder to write down the formulas, but again, who cares? Okay. How big are these little pieces? If I have, again, on my interval on the x-axis, if I look at a particular subinterval there, and on my interval on the u-axis, if I look at a particular image subinterval there, how big is this? How big? What's the formula I can write down for delta u? Well, here's the formula that y'all may recall, again, from the substitution rule. We write, in Calc 1, we'd write du equals g prime dx. Where does that come from? Why is that the formula, other than the algebra seems to look like it sort of suggests it. There's a really easy way to see why this is, and that is to observe that sizes, right? If I think of this delta x as telling me the size of that interval, I can reinterpret that size as a change. Think of delta x as the amount that you change the value of x in going from the left endpoint to the right endpoint. And likewise, the size over here, again, let's reinterpret that as a change. And let me just remind you then that we have an existing concept for how to turn input changes into output changes. And the relationship between input changes and output changes, I hope you all are getting knee-jerk flashbacks to chapter 13. That relationship is the derivative. So, bam. That's why you multiply by g prime. That's the way I want to encourage thinking of it here. Okay. So, with all that groundwork laid, observe if you have a Riemann sum over here on the interval on the u-axis. Everything that we have written over here in this Riemann sum, all the algebra in here, it's all in terms of u, but all these things in terms of u I can rewrite now in terms of x. So it's just sort of an observation that, for example, delta u, there's our formula for delta u. It's g prime of x delta x, right? And approximately. And this u here is g of x. After all, that was my formula. So everything that's in this Riemann sum on the right, I can rewrite as in terms of x, and notice that gives me a Riemann sum in terms of x. That gives me, therefore, an integral on the x-axis. It gives me a dx integral. Okay, so this is the point of view I want to encourage, right? This is not the way they present the substitution rule back in a Calc 1 or Calc 2 class. I know in Calc 1 and Calc 2 they present it as, let's treat these differentials as if they're actually independent algebraic objects. They kind of sweep under the rug how they make sense out of that. But nevertheless, that's how they present it. And look, it gets you to right answers, and it's sort of satisfying in that sense, right? But this is a little bit more explicit picture of what's really going on there. This is going to be an important segue for what we're doing for the change of variables that we're about to start talking about. The big takeaway that I want you to get, there's two big takeaways of this argument. Oh, by the way, I forgot to spike the football. This Riemann sum is that integral, that du integral, and this Riemann sum, of course, is that dx integral. And so therefore, we have, in the process of turning that Riemann sum into that Riemann sum, we have confirmed the substitution rule for integrals. Old news. Okay, so two big takeaways. Here's the first one. This process of turning a u integral, a u Riemann sum, into an x Riemann sum, or x integral, we call that a pullback. I call that a pullback. The reason for the terminology is, don't forget, the function g kind of goes the other way. So it's something kind of counterintuitive about this. Isn't this function g supposed to turn x's into u's? It does. Now, you give me an x, g gives us a u. How come it's going the other direction here? And the important point is this is what happens. This is what plugging in does, right? The process of plugging in takes things the other way. We're not taking values of x and resulting in values of u. We are taking expressions involving u and plugging in, and there it is right in front of you, where we clearly get as a result an expression involving x, right? So the function takes values left to right, as I have it drawn here. Plugging in takes expressions right to left. It's just how plugging in works. So I think it's nevertheless, it remains a little bit sort of like head scratchy. That seems weird, it seems backwards somehow. So this is worth having a name to recognize what's going on with this construction. The word that I like is pullback. So heads up, we're going to talk about another pullback momentarily, and then later on in the course, even more pullbacks. So this is a big idea. Be on the lookout for pullbacks. The other takeaway I want you to get is what I like to call the stretching factor. Stretching factor. This is the factor that we multiply by that size, delta x, to get this size, delta u. Right? In this process of taking that x interval and putting it into the g function and doing what g says, it gets all contorted and maybe shifted, but also stretched out a bit. And this g prime is the factor that tells you on each little piece how much did that little piece get stretched by the function. So stretching factor, common term. I'm not the only one who uses it. That's the second big takeaway. Okay, so stretching factor and pullback are the big takeaways. Now, this is all single variable calculus. We're in a multivariable calculus course, right? So why are we doing this? And this is all to lay groundwork for the hope that we can do something analogous in a multivariable setting. And so here's the big idea. Let's suppose that I've got some function, a multivariable function. And let's think about a domain over here, right? And its image over here. If I found myself with an integral that I want to compute on that domain, can I do kind of what I did just a couple of pages back? Can I use my understanding of that g function in whatever is the appropriately adapted manner, details, we'll talk about that in a minute. Can I use that g function to pull back an integral on that purple domain and turn it instead into an integral on this green domain, which, by the way, I like much better. After all, it's a rectangle. I love rectangles. They sure are easy to slice up. Okay. So that's the big idea. We want to be able to do just a kind of an analogous thing. We want to pull back through G to turn a purple ugly integral into a green nice integral. Yes?
I feel like, wouldn't we be able to compute the green integral without going over and then coming back?
Oh, yeah, no, but that's not the question. The question is, suppose we start with an integral on the purple domain.
Oh,
yeah.
Okay.
Yeah, no, that's right. It's you're quite right. If we already have an integral on the green domain, then life is good. Let's go ahead. Yeah, totally. Right. Okay. So that's the plan. That's the hope, right? And there's like I say, some details to be worked out. But the short answer is, yeah, sure, absolutely, totally works. It's fine. Go ahead. Right. So the area that we talk about over here. Oh, I'm getting my colors mixed up. The area that we talk about here, I'm going to call it dA because I want to think of this as a double integral, not an iterated integral. But don't forget, the dA that I'm talking about over here, it's area in the xy plane. If I were to write this as an iterated integral, it'd be dx dy, right? But think of it instead as dA. That relates to a little piece of area over here, dA. Now, my pullback domain, arbitrarily, I'm going to call the UV plane. So du dv. Right? And the relationship is, well, it depends on how much does this function stretch things out. That function there is going to stretch areas by some factor that we haven't figured out yet. I don't know what that is, but once we identify it, we'll be able to just rewrite xy area in terms of u's and v's by just knowing the stretching factor. And then correspondingly, right, I mean, don't forget, of course, this g. G gives x and y as functions of u and v. So, well, after all then, x and y are g of u and v. So don't forget to plug that in. That's just plugging in, though. I mean, that's nothing new there. But you do so, and just like we did in the substitution rule case, everything that was initially written in terms of these variables on the right, by plugging in, we've now rewritten it all in terms of variables that are on the left, and we have ourselves a new integral over a new domain that's nicer, and victory, right? It's totally going to work. We just have to figure out what is the stretching factor, and I'm going to delay my explanation of where the formula that I'm about to show you comes from. I just think it works out better to talk about that motivation later, but I'm going to just tell you what the formula is, and here it is. The stretching factor is the absolute value of the determinant of the Jacobian matrix. And there's good reasons, and we'll talk about those later. Okay. So don't forget the Jacobian matrix is it's this formula here. It's the same Jacobian matrix that we used when we were talking about the chain rule, right? And if you were to write its determinant, don't forget that we have a little formula for determinant, right? Determinant is that times that minus that times that. Nice little formula, which you'll notice. What you will notice eventually in writing this down a bunch of times is that formula is, in fact, all of the partials of x and y with respect to all of the input variables u and v, and it ends up just being a really convenient way, a convenient way to represent this determinant is that determinant is we just write it with this notation here. This is just notation. It is very convenient notation. I do encourage it. I'll explain why momentarily. But partial x comma y over partial u comma v is really handy. Shorthand for what we're actually doing here. So don't forget what this notation means. It means compute the determinant of the Jacobian matrix. But we're going to write it like that. Okay. All right. So that's the thing you take the absolute value of. Now I have to emphasize, don't forget to take the absolute value of that Jacobian determinant. Okay, side note, this is just a notation thing, but unfortunately the book refers to the determinant as being the Jacobian. It's just notation. I guess it's fine. In the way that they use it, they're clearly using it as a scalar. So surely it's clear that they didn't mean that that's the matrix, right? So anyway, I think that's a little confusing. I think it's important to be able to refer to the matrix itself as the Jacobian because, after all, we actually do things with the matrix itself. I can't just afford to not have a reference to the matrix itself. So I like to actually explicitly write determinant of the Jacobian. Okay, that's just an FYI. It's just notation, nothing to worry about. Okay, so let me show you why this notation is so convenient. What we have up here, right, is that this dx dy is our stretching factor times du dv. Right, so this is what we're really doing with that stretching factor, and check it out. This is really convenient. Let me zoom in for emphasis. If you were to write this stretching factor as partial xy, partial uv, it's as if those cancel, and then you see that's reminiscent of that. And so it's highly suggestive of the, writing it as a fraction is highly suggestive of the factor-like purpose that it serves, right? So that's pretty darn convenient. You're going to find that even, computationally, there's a situation that's going to come up very soon where that's, in fact, extremely helpful and will help us keep certain things straight. So I encourage this notation. Now, I want to emphasize this is not actually a fraction, right? I mean, it says so right here. Let me zoom back out. That is a determinant. Determinants are not fractions. So it's not a fraction. This cancellation that I just did right there, I mean, I got the creeps when I did already, because it's not actually a cancellation, right? It's not a fraction. Just to emphasize, this thing by itself, that's not a thing. Right? So none of the actual little argument that I made there is complete garbage, but it is very satisfying that it's as if that happens. So anyway, don't buy too much into that, but feel free to be consoled by it. I'll say it that way. Okay. All right, let's see an example. Let's compute an integral on the following ugly domain, R. Want to compute an integral on that domain? Let's go ahead and recognize, just for effect, what a nightmare it would be to do an integral on this domain sort of straight up. Because after all, if you as you're doing your slices, you'd slice through a corner there, and then as you keep doing your slices, you'd slice through a corner there, and then etc. So you'd have to write down 3 separate integrals here, and then you might think, okay, well, I'll do it the other way. I'll slice this way. Well, again, you slice through a corner there, and again, you slice through a corner there, and so again, you've got 3 chunks. So this is inconvenient at best. Okay, so there's our domain, and now the domain is given. You'll notice this is just a starter example, by the way. It's given as the image by way of this function that I'm calling g, right? Specifically the image of the unit square. So the way the problem is given, right off the bat, we see it's kind of ripe for a change of variables argument, because after all, we're given the pre-image, the pullback domain, right there in front of it. The change of variables function g is given, right? This is totally ripe for change of variables. They won't all be like this. Questions will come up. How do I find the correct change of variables function? I'll talk about that as we go along. How do I find the pullback domain, etc.? So there's various different circumstances, but it turns out that very often there are good answers. So anyway, for the moment, I just want to get the mechanics dealt with. So how do we actually do this? Well, we're going to be using this formula right here. Right, there's our change of variables formula. Our stretching factor, we have a formula for. The stretching factor is that Jacobian determinant, absolute value. So let's compute that stretching factor. The stretching factor comes straight out of this formula. I've got x and y as functions of u and v. This doesn't quite fit, does it? And here you go. Say it like that. You write down the Jacobian matrix. You take the determinant. I forgot to write determinant. Shame on me. Yeah, there you go. It's just algebra. There's one little tricky bit here in computing this stretching factor. It has to do with the absolute values. Don't forget the absolute values are required, right? You can't avoid those absolute values. And so we find ourselves looking at the absolute value of 4uv minus 9. And what is the absolute value of 4uv minus 9? Well, it depends. Is 4uv minus 9 positive? Or is it negative, right? And if it's negative, then you got to throw in an extra minus sign because that's what absolute values do. So how do you know if 4uv minus 9 is positive or negative? And the answer comes from the fact that I know u and v. I can see them right here. There's u. There's v. My domain right here tells me that I can see here u is always between 0 and 1, right there in the picture, right? And v, likewise, is always between 0 and 1. I can see it right there in the picture. So looking at this expression here, 4uv minus 9, well, no mystery at this point. u and v are both between 0 and 1. That means 4uv got to be less than 4. And so you subtract 9, it's definitely going to be negative. So this expression, definitely negative, and the absolute value of a negative is the negative of itself. So that's what happens, those absolute values. Please don't just kind of drop the absolute values and try to be inconspicuous about it. Right? That doesn't work. That's a completely invalid argument. You got to address the matter. Okay. Having done that, it's all plug and chug at this point. Specifically, let's see here. X. There's X. Whoops. Okay. Well, man. Anyway, here's X. Right. X is that. And then here's Y. Right? Don't forget the change of variables function itself is what you're going to plug in with. So Y is that. Don't forget to put in your stretching factor. dx dy is stretching factor times du dv. We just computed the stretching factor here. And success. We've turned an integral on a terrible domain. We turned an integral here on a terrible domain into now an integral. Hey, it's got some algebra in it, but this is an integral on a nice domain, right? Check it out. The domain integral from 0 to 1, integral from 0 to 1. It's a rectangular. It's a square. It's a unit square. It's the world's best domain, right? So big victory. Right? We don't have to do 3 ugly integrals. We only have to do 1 not very ugly integral. Everybody good? Okay, so this is a good place to draw the line. We will pick up here on Friday. See y'all later. Oh, and as usual, if I didn't get you on a text.